Okay, so part 2 of 6.6, part 2. And this is going to be about beta decay in the neutrino, and a small little bit on electron capture, which we're just going to briefly mention here at the end. So let's first focus on the beta decay. So far we've talked about beta decay, and we've looked at it in terms of this reaction right here. But if you think about it, we sort of stopped it right there. If you look back a couple chapters, you'll find that they actually put this part in here, the antineutrino. Yes, the antineutrino in there, but we haven't had to be really responsible for it yet. So now that we're in this option, we have to be responsible for it. So this is the decay of a neutron, and it decays into a proton plus an electron with a -1 charge. You can see there, but no mass. And then this little neutrino, antineutrino, the bar over it indicates antineutrino, is given off as well. Now there's another reaction that they found, which was called positron emission, and this is where a proton decays into a neutron plus a positron. Notice that part right there. It's a positive, so it has basically the properties of an electron, but it's positive. And so it has, the mass, and it's just that the charge is the opposite. And then this yields a neutrino. So notice that these neutrinos have 0 mass and 0 charge. So here's what we're going to talk about. Wolfgang Pauli, love that name, and he later came up, I don't know if it was later, I'm sorry to come, but with his Pauli's exclusion principle, and Enrico Fermi both looked at these equations and thought that when you added up the energies, so when you added up all the energy on one side of the equation, you had a little bit of a discrepancy of energies. So they were wondering where is the other energy going. So in other words, they couldn't find it in the electron and the proton together. So they hypothesized that there must be another particle that takes up this energy that gives off this. That uses up the energy that's being released during the decay. So let's sort of take a look here at. So what are you responsible for? So you need to know these equations and know the difference between a neutrino and an antineutrino, and a positron and an electron. So this is pretty simple. So in the nucleus of an atom, remember this is nuclear physics. When a neutron decays, this is what it decays into, and when a proton decays, that's what it decays into. Positron emission and electron emission. So here's sort of how they hypothesized it. They basically added up all the energy on one side, and then they subtracted it from the energy of the particles. So in this case, it would have been like energy of a neutron plus the energy of a proton in beta decay, right? Plus the energy of an electron, and they ended up having a little bit of extra energy, and they were wondering where that energy came from. So here's basically what they think of is, so you don't need to know any of the math or anything. You just need to be able to state the ideas behind why. What does it say? I'm just going to read it here. State the theoretical arguments that have been used to postulate the existence of the neutrino. So there, basically, there's one that excess energy, it has to be kept somewhere in a particle. So let's think about what happens if a neutron decays. So if a neutron decays, so here it is sitting at rest. Let's just imagine it at rest. Now I'm going to move it over here to the right a little bit. If it decays, then you get a proton going this way, and that, remember, the electron would go this way. So I'll make a small little electron there. And so if you think about that, well, if that's the case, then the sum of, now remember that the momentum initial was equal to 0, so the momentum final must equal 0. So that means that these two particles must have the same momentum, and for that small electron to have the same momentum, it must have a huge velocity. And therefore, most of the energy is in the electron, and that's because 1/2 mv squared equals ek. And remember, velocity is a much bigger key player than the mass in this case. So, because it's squared. So, so just thinking in that regard. So that's a simple case. But what they were finding is when these things shot off is that they found that when they looked at the energies that they actually measured from the electron energy, they found that it was not equal and opposite, and so they were wondering where that particle could have went. So that leaves a simple scenario. That's a very simple scenario. And then another scenario would be, well, what happens if it decayed into 3 parts? So now you have this part going maybe off this way, and another part, the electron, maybe going this way, and then you have a small little neutrino going this way. So, but it's endless possibilities of what could happen here, because they could go in all different directions. Whereas before, think about that, wherever the proton went, the electron had to go exactly equal and opposite, because the 2 momenta had to cancel, or the momenta had to be 0 afterwards. So in this case, when you added up all these vectors, you'd still get a net momentum change of 0, and that would well, anyway, so in this case, you could actually surmise that there must be another particle, because especially if the electron went off at some other angle, and that's what they were seeing, is that the electron didn't go opposite of the proton. It went off at some other little angle, and they knew that couldn't be, because then how did the momentum get canceled out? You see what I'm talking about? So if the particles went in, if the proton went off in this direction, and then the electron went off here, well, wait a minute, that can't be true, because now the momentum after is not 0, and that doesn't obey the law of conservation of momentum. So that led them to the idea that there must be another particle there. And they named that the neutrino. That's a U. And remember what that stands for? The little neutral one. And if you want to look up Fermi, if you go to the University of Chicago and you look up the Fermi lab, he has he's long dead, but he has a particle accelerator up there outside of Chicago, big circular one. You can actually look at photos of it through Google Earth, and that. If you just put in Google Earth and put in Fermi lab, you'll see the actual underground tunnel that causes the that was one of the first particle accelerators made. So pretty neat that he's up there at the University of Chicago, and wouldn't want to be in Chicago though right now. I think it's still below 0 up there. Although it's pretty cold outside here too, isn't it? Okay, so going forth, and let's sort of wrap this up. So the electron capture. They just want you to know the basic here of an electron capture. Basically, what they're saying is that a proton, in some cases, can capture an electron, and when it does, of course, we know that, think about it, it's the exact opposite of beta decay. A neutron becomes a proton electron, then it becomes a neutron and a neutrino. Okay? Now, a couple things I want to say here. First, don't think that a neutron is just a proton and an electron, and in an electron. Or that these subatomic particles are just made up of, like, oh, if I have a proton electron, I can put them together and make a neutron. It's not like building blocks like that. It just happens to be energies that are different. So, in other words, just don't think that these particles, that if you add them together, you automatically get that. So, what about this electron capture that they want you to know? Is basically, this is how neutron stars are formed, and that the outside pressure pushing in can literally drive that electron into the proton, because it doesn't want to go there naturally. It wants, so how do you get it to go to it? And then the outside pressures, the large pressures, that you'd have from the star, and then on the inside, you could literally drive the electron into the proton, making them into neutrons. And so basically, that's really it. The biggest thing that you want to take with you as I wrap up here is that the energy that they basically thought they should get of the electron, which I think, if I can remember, I think it was like 0.783 MeVs. Ooh, I'm putting that in a bad place. Let's separate this, okay? Has to do with neutrino. So that was the energy of an electron. But when they looked at it, they did not get that. They got ranges of electrons. They got some, maybe some in a perfect case maybe gave that much, but they got ranges up to that. And so what did that tell them? Well, when they looked at the energy that they should be getting of the electron, it should have been something like that, but it was not. So since it was not, where did that other energy go? And that other energy went into the kinetic energy of the neutrino. And that's where that little vector diagram helps you understand that. Okay? We'll do a brief discussion of this again tomorrow. All right, stay dry and warm, and I'll see you tomorrow, and hopefully we'll have a great weekend.